Okay, in this video we're going to look at the special case of motion when the acceleration is constant. The reason that we're going to do that is because very often this happens in the real world. The acceleration is constant in many different situations. And so it's worth spending a little bit of time focusing on it and really focusing on understanding what goes on when the acceleration is constant. And what we're going to see, this is a little bit of a preview, is that there are very simple equations that describe the motion of any body when the acceleration is constant. In fact, there are only 4 of them. And so this video is dedicated to deriving those 4 equations and showing you where they're coming from. And then in subsequent videos, we're going to work lots of examples so you can see lots of different applications of these 4 equations. Okay, so first let's consider the definition of acceleration. And there's a weird thing here, WLOG. I wanted to put that in because I wanted you guys to see it. This is something that you see on a lot of physics type proofs, and it means without loss of generality. And what that means is we're going to, just as an example, we're going to show how this works in 1 dimension, but everything that we prove for 1 dimension can be extended and proven to work just the same in 3 dimensions. I'm not going to bother doing it in 3 dimensions because it's really messy and there's just a lot of terms you have to keep track of. And it's not harder, it's just more tedious. And so we're just going to consider everything moving in a straight line, let's say along the x-axis. And we have a definition that the average acceleration is delta v over delta t. That is our definition of acceleration. But if the acceleration is some constant value, let's say a, then the average of all the possible a's, which is constant, is just going to be a. And so that way we can go from the average acceleration being delta v over delta t to being just a is equal to delta v over delta t. So now we can do a little bit of algebra. We have a is equal to delta v over delta t. If we multiply both sides by delta t, then I'll have a delta t up here that cancels, and I'll have a delta t over here by this a, and I can rearrange this, and I'll end up with delta v is equal to a times delta t. So that's just an average. I've just moved this delta t over next to the a, leaving a delta v by itself. Delta v is a delta t. But what's delta v equal to? That's just v final minus v initial. So I can plug that in, and I can say that v final minus v initial is equal to a times delta t. And if I bring this v naught over, I solve for v final, I have an equation that tells me that the final velocity equals the initial velocity plus the acceleration times the change in time. And this equation is kinematics equation number 1. Now, before we go on, I want to remind you of our fundamental assumption. Our fundamental assumption is that the acceleration is constant. This equation does not work if the acceleration is changing with time. But if the acceleration is some constant value, 10 or 14 or 22 or minus 7 or whatever it is, but some constant value, then this equation holds. The final velocity is equal to the initial velocity plus the acceleration times the change in time. And that is kinematics equation number 1. And I do expect you guys to know that. You're going to have to memorize these kinematics equations. It's just, there's no way around it. You just need to know them. So let's look at an example of using this equation. We can say a mass of 12 kilograms starts from rest, and it has an acceleration of 3.5 meters per second squared. The question is, what is the velocity at 3 seconds? And so here we have a final time, which is 3 seconds, and it's starting at time equal to 0, obviously. The final velocity is the initial velocity plus at. So what is the initial velocity? If we look in our problem, it says it starts from rest. That means the initial velocity is going to be 0. And so the acceleration is 3.5. We can plug that into A. The change in time is going to be 3 seconds. If we start from time equal to 0 and go to time equal to 3 seconds. And so if I plug all of those in, I get that my final velocity is 10.5 meters per second. And you can note the units here because you're going to see that I've got meters per second in this first term because it's a velocity, In the second term, I've got meters over seconds squared times seconds. And so one of those seconds squared is going to cancel with that second and leave us with meters over seconds. And that's what the units have to be for a velocity. Now, there is one thing that I want to add to this, and it's an important idea because I've written this equation as v final and v initial, but this can be a little bit limiting. Very often you'll see it written without the final. It'll just be v is equal to v naught plus at, and this v is really v of t, v as a function of time. In other words, this equation, if you think of this just as the final velocity, and a lot of problems, that's the right way to think about it. It makes it easy to understand what's going on in the problem. But there are other problems where there might be multiple final velocities that you have to calculate, and it can be confusing, which one's really the final velocity and so on. In this case, it's better to think of this as v as a function of time. And what that just means is that if you plug in any time here, then that will tell you the velocity at that time. So for every possible time, you can know what the velocity is. So instead of thinking it as one final velocity, it's whatever velocity you need. Whatever time you give me, I can tell you that velocity. Now, if we think of v as a function of time, we can plot velocity versus time. So I have the velocity is like the y-axis, and time is like the x-axis, and my equation, my velocity function as a function of time, is v naught, the initial velocity, plus at. Now v naught is just a constant value, and a is the acceleration, and t is the time. But if I plot v versus t, velocity versus time, this equation actually looks a lot like y equals b plus mx. That's the equation for a straight line, and you can see, indeed, the plot of this function is given by a straight line. Now, in this formula, b represents the y-intercept. So in the function that we're plotting here, the v naught, which is like the b, that's going to be the intercept of the velocity axis. And if we think about that, look at the time here. The time axis, this is when the time is 0. So v naught is the velocity when the time is equal to 0. And that's going to be the intercept of that vertical axis. Now, the a here in the equation, that corresponds with the m. So you've got v naught plus at. T is what you're plotting. Normally you plot x, but here we're plotting t. A is like the slope. And let's look at the slope, because if I go from this point to that point, I'll have gone over some delta t, and I'll have gone up some change in velocity, delta v. And if I do delta v over delta t, the rise over the run, that would be the slope. But that's also the definition of acceleration. A is equal to the change in velocity over the change in time. And so the rise over run that we see is delta v over delta t. That's just the acceleration. And so we can see that in the formula too, that that's the slope. This is a very important idea that we've seen before, but we want to keep it in mind that the slope of a velocity versus time graph is always going to be the acceleration. And in this case, the slope is constant because it's a straight line. And we know that because this is our kinematics equation, which only works when the acceleration is constant. Now, there's another equation, another relationship that we can talk about, and it's the one that's boxed here. The average velocity equals the final velocity plus the initial velocity divided by 2. So we have there the final velocity, initial velocity added together and divided by 2. So let's look at our graph again. We have some velocity, that's an initial velocity at t equal to 0, but the object is accelerating, it's speeding up. And so if you go to some later time, which we'll call t final, the velocity will have gone up to some velocity that's a final velocity, which is at that point here. And so we can measure the final velocity by going straight across to the vertical axis. We can measure the time when that happens by going down to the time axis. but this velocity is the final velocity, and this velocity is the initial velocity. And if we wanted to just average those two velocities, the one that's the initial and the one that's at the end, those two would average right smack dab in the middle. And we'll pretend that that's right in the middle of that line. So if this is the average of those 2 points, the initial and the final, that's not really particularly useful. But it is that, but it's also more than that. And it is something that's useful. Because let's consider it's a property of straight lines that if you're in the point in the middle, like this little x that I've drawn for the average, this, if I move this over here, this would actually be the point v average. So that would be the average value of the velocity of the endpoints of the motion, the initial and the final velocities. But if I pick a different point on that line, let's say this point, there has to be a corresponding point below that is the same distance away from the middle, so that these two green points would average to be what you have in the middle. And if I picked another point, there would be another point down below that averaged to the middle. Every point that you have above has to have a point below, because that middle point is in the middle. And so that means that all the points on this part of the curve has to have a corresponding point below that all average to the middle. That means that this equation here isn't just true for the endpoints, it's true for every point on that line. It's generally true that the average velocity over the entire time interval is given by this formula. And this is another kinematics equation. Now, this equation isn't used very much actually. It's important to know, but later on we're going to list all of our different kinematics equations. Because this is the least useful of them, we're going to stick it on the end. Even though we covered it second, we're going to make this is going to be kinematics equation number 4. But we'll see that when we get to the end of the video. Okay, right now we have 2 of the equations that we want to develop. We've got 2 more to go. And so at first we considered the definition of acceleration, and we did some algebra, and we came up with our kinematics equation. Now we're going to do the same thing, but we're going to consider the definition of velocity. Velocity average is displacement over time. And so we can say that delta x, if I solve for delta x, that's going to be my average velocity times the change in time, delta t. But we just saw that the average velocity is v final plus v initial over 2. That's why, even though this is the last equation in our list of equations, we went ahead and derived it because we needed it to come up with this final equation. So anyway, we've got delta x is v final plus v initial over 2 times delta t, but v final, this guy v final, is equal to v naught plus a delta t. That is our first kinematics equation that we developed. And so if I plug this guy in for there, I end up with delta x equal to 1/2 v naught plus a delta t plus v naught, all in parentheses, times delta t. So I've just plugged in for my v naught here, and I pulled the half out front. So look at what I have here. I've got 2 v naughts here, and I've got my delta t there. And so I can multiply all this out, and what I end up with is that delta x is equal to 2 v naught times 1/2, which is just going to give me v naught, which is going to be then times this delta t here. And so I've got v naught times delta t, and I'm just going to call it t because usually our t naught is 0. And then I've got 1/2 at delta t, so that's going to be 1/2 at squared. Now keep in mind that this delta x here, that's x minus x naught, and so I can take this, so I've got x minus x naught is equal to v naught t plus 1/2 at squared. I can bring this x naught to this same side of the equation where it'll become positive, and I end up with my second kinematics equation, x equals x naught plus v naught t plus 1/2 a t squared. And this is my second kinematics equation. Okay, so we've got a couple of very useful equations. There's one more that we want to develop, and it's going to prove to be very useful. Now, we have our relationship that delta x is equal to v average times the time, and we can plug in for v average. We know that v average is equal to v final plus v initial over 2. And to get t, we can solve our first kinematics equation for t. And so if I bring the v naught over there, it becomes negative. I divide by the a. I'm basically solving this whole equation for t, and I get that t is equal to v final minus v initial over a. So for v average, I'm going to plug in this equation there. And for t, I'm going to plug in that equation there. And so I get my delta x here. Delta x is v final plus v initial over 2. And then I have v final minus v initial over a. And look at what I have. This is something that I can FOIL out. And when I FOIL this out, I end up with delta x equal to v final squared minus v initial squared over 2 times the acceleration. And then I can simply multiply both sides by 2 times the acceleration to get rid of this denominator, because I want to solve for this guy. And so I get 2a delta x is equal to v final squared minus v initial squared. Now, just to point out, I just multiplied these guys out to get that. This is a difference of 2 squares. So usually you're probably used to going backwards. If you're given v final minus v initial squared, you know that you can separate that to v final plus v initial times v final minus v initial, difference of 2 squares. But if you FOIL it out, this is what you end up with. And then I simplified, and then if I've got this negative v naught squared here, if I bring it over there and solve for the final velocity, I get the final velocity squared is equal to v naught squared plus 2a delta x. Now, that is our third kinematics equation. So let's sum up. These are our 4 kinematics equations, and you need to learn them. You need to understand what all the parts of them are. You know, what's v naught? It's the initial velocity. What's x naught? It's the initial position. What's a? The acceleration. T is the time. The v average is the average velocity. These are things that you need to know. Delta x is x minus x naught. It's the displacement. Know what all the parts of these equations are and memorize the equations themselves, and also memorize the number or the order that they're in. This is equation 1, number 2, number 3, number 4. And so that way in the future, if I say we're using the second kinematics equation, you know we're using the position one, this one. If I say we're using equation 1, you know we're using the velocity one, this one, etc. So you definitely have to memorize these equations. You need to know them in order, and you need to know what all the parts mean.